Okay, so we've been talking about similar triangles for the last 2 days. And you may remember when we talked about congruent triangles, that there were only a few theorems that allowed us to prove triangles are congruent. What was one theorem that allowed us to say, that means that the triangles are congruent?
Side angle side.
Side angle side. Someone else give me a different one.
Side.
Side. Someone else? Angle side angle. Someone else? I think that's the same person. We already said it. Give me someone new, someone different. Angle side. Good. Someone new. One more. We got angle side angle. RHL, good. And you remember that there were two that we wouldn't use of these, like the letters labeled. AAA we didn't use, and ASS we didn't use. Ooh, we can't say that in math, right? This one was the redundant case, or the ambiguous case where there's two possible triangles. Why didn't this work? It can be enlarged. So that's what we're doing today, is we're talking about what if they are enlarged? What if they're the same shape, but they're just different scale, dilations of each other? Then if we had all three angles, that would be enough to say they're the same triangle, just a different size. And in this effort to reduce how much effort we need to put in to be confident that they're similar, we don't actually need the third angle, do we? If I've got two triangles, and I know that this one's got a 50 and a 60, and this one's got a 50 and a 60, isn't that enough to know that the third angle is the same as well? Yeah, you might remember from our triangle angle sum theorem, we actually had a corollary to it that said if two angles of one triangle are congruent to two angles of another, then the third angles must also be congruent. So we really only need two angles to be congruent, and that would give us similarity. So for today, let's start with that. Here's a picture of two triangles formed by some parallel lines and such. Are they similar? Well, I've started with the notes here to show you that yes, they are similar, but in order to make them similar, we have to justify it using the angle-angle similarity concept. So what angles are congruent in here now? CED is congruent to what? GEF. Love your use of terminology. How come you know those are congruent? They're vertical angles. Good. What else? Is there another pair of angles that's congruent? Owen? Okay, why would those be congruent? Excellent, I like that. And so when we do that, we're talking about CG as the transversal. So we're going to say it's this one down here, right? ECD and EGF. That way, relative to this perspective and this transversal, those two pink ones are alternate interior. They've got to have a same transversal. So that's enough for us to say that these two triangles are similar by, and then here's the rule we write in, A similarity. You have to put that little similarity symbol there, please. Once we've established that they're similar, we get to claim they're similar using the similarity statement. If I'm saying CDE is similar to what triangle? Is it FGE? Is it EFG? Is it GEF? How do we know? Do we agree that C is already marked as the pink one? What's the corresponding one over here? G. So if we began with C here, don't we have to begin with the corresponding one, or G here? And then from the C, we went along the parallel line to get to D. So from G, we'd go along the parallel line to get to what? F. And then the third piece would be E. That's the similarity statement. We'll also see shapes like this, number 3. And forgive me for my typing here. I typed over the top of this, but the original shape just had a right angle, 39 degrees, and then nothing up there in the corner. And this one over here has a right angle and 51 degrees and nothing in the corner. So are they similar?
They could be.
I like the openness to them being similar, but can we prove it? If I take this angle S and this angle E and this angle Y, what do they all add up to? 180. So if I take S and 39 degrees and 90 degrees, those should add up to 180. And if I subtract 39 and 90, what I get is that S is equal to 51 degrees. And this is 51 degrees. So now don't I have 51 degrees here and 90 and 51 degrees here and 90? Isn't that enough? I can say yes, similar by angle similarity. And now I need to create my similarity statement. What triangle is similar to WHC? Good. 51 degrees is where I'm starting for W, and that's my S. And then I'm going to not the right angle. So I'd go to not the right angle, and then finish on the right angle. Any questions on using angle similarity to validate that triangles are similar? Okay, you'll remember from last class, we talked about the definition of similar polygons as not only having corresponding angles congruent, which is what we've just been working with, but also that corresponding sides are proportional. So that's this next one, SSS. If we can establish that all three sides are in the same scale factor, in other words, I multiply the same amount times any side on the small triangle, and it takes me to the corresponding side of the bigger triangle, then I know that those triangles are similar. But here's the challenge. Am I looking for 9 going up to 31.5, or 9 going up to 21, or 9 going up to 14? How do I know how they correspond in a line?
You could see that the hypothesis is always bigger congruent.
I like your idea of using size because it's very distinct in a triangle. We can't use the word hypotenuse because that refers to a right triangle specifically, and we don't know that with certainty. But would you say this 9 is the smallest, the mediumest, or the largest side? So what's the corresponding side over here? 14. Those two line up. And 13.5 is the what? Mediumest or the largest? What's the mediumest over here? 21. So those two line up. So we can create a proportion, like we did last class, to see if 9 is to 14 as 13.5 is to 21. But how do I know if these are the same? If only we had some cool technique to validate that a proportion is, in fact, a valid proportion. Something that you did like 10 times in yesterday's homework. Cross multiply, excellent. In other words, we can say that 9 times 21 should equal 13.5 times 14. And if in fact that comes out to be a consistent answer, it does, 189 equals 189. That tells us what? Oh, that's enough to say the triangles are similar? How many pieces did we get there? 2. We got this pair of sides, the yellow ones, and we got this pair of sides, the pink ones. So in terms of our side similarity, we've gotten our S, we've gotten a second S, but we need another thing, don't we? We need a third one. So somehow we have to validate that these two are in that same proportion. In other words, 20.25 is to 31.5 as what? We could do 13.5 over 21, or we could do 9 over 14. It doesn't matter, does it? I do have to make sure that this fraction makes sense, right? This is the smaller triangle over the bigger triangle. So this has to be the smaller triangle over the bigger triangle. And then I cross multiply. And let's see, if I take 20.25 times 21, I get 425.25. And 13.5 times 31.5 is 425.25 as well. There we go. That gives us the third piece of information sharing the same proportion. Therefore, that gives me my third S, and I can say yes by side, side, side. And please, please, please make sure that when you write this, you don't just write side, side, side. Put the similarity symbol on it. Because this theorem and this theorem are two entirely different things. I know they're so closely written, but if I say this one in words, it says, if 3 sides in one triangle are congruent to 3 sides in another triangle, then the triangles are congruent. This little tilde down there changes this entirely to say, if 3 corresponding sides are proportional, then the triangles are similar. So the hypothesis is different and the conclusion is different. Would you, oh, and then let's do our similarity statement. So what should we call this triangle? Does it matter? NRK, sounds good. First one was free, but now it's going to be restricted. How would we describe N in terms of our colored sides? Yeah, in between the medium and the smaller, in our case, pink and yellow. So what over here is in between pink and yellow? E. And then from N, we traveled over to R, which is along the pink. So from E, we go to S along the pink, and then to D, ESD. A little messy in there, sorry about that. Would you guys please try number 8 yourselves? Please demonstrate that those two triangles are similar by side, side, side similarity. What's the twist in this one that can make it a little bit difficult? You got to look at the triangles themselves. So in other words, we've got this little bitty triangle with 15, 30, and 20 as the side lengths. And then we've got this bigger triangle. And how long is the side length that corresponds to 15? 21. This is 42. This is 28. Make sure you use those numbers in setting up your proportions. All right, can somebody help me set up the first proportion?
15 over 21 times 20 over 28.
15 over 21 equals 20 over 28. Okay, I've got it set up to be small triangle over big triangle. That looks good. So I'm going to multiply those. I'm going to get 15 times 28 equals 20 times 21. Now, I'm just going to go off on a little tangent here. And let's say that you're stuck on a desert island trying to do this. And you don't have a calculator. Are these two products the same? So here's a kind of cool way to do it. Yes, you could multiply them out, but can you factor 15? What is it? 3 times 5. Can you factor 28? 4 times 7. What about 20? 4 and 5. What about 21? 3 and 7. Are these the exact same factors? 3, 4, 5, and 7. 3, 4, 5, and 7. So doesn't that mean the products would be the same? It's kind of a cool way to think about comparing two numbers. Instead of multiplying them out the long way, take them backwards. So are we done? Does this show they're similar? No. What do we have now? This is 1S. What's this? A second S. What do we need? We need a third S. How am I going to do that? Yep, could have chosen either one, right? So now I've got 30 times 28 equals 20 times 42. So this is 3 times 10 times 4 times 7. This is 2 times 10 times 3 times 7 times 2. So that's going to work out as well. That gives me my third S. So yes, similar by side, side, side similarity. WVX and WY. Quiet, please. Any questions on using side, side, side similarity to prove triangles are similar? Flip to the next page. The third and final way that we're proving triangles are similar is side angle side, where we've got one pair of sides and an angle trapped in between. So for example, what can I match up this 24 with? Why 6? You're right. Yeah, it's the smaller, right? Of these two here, if in fact they do match up, then the smallest one would match with the smallest, and the biggest one would match with the biggest. But that only gets me how many sides, how many S's? Well, the yellow is 1 and the orange is 1, right? So anytime you get 1, you're going to get 2, because what you're saying is they both have the same proportion, same scale factor. So what do I need to finish this off? And given the fact that this section is called SAS similarity, what do we think is missing here? Do we see an angle pinched in between these two? Yes. Why are these angles congruent? They're vertical angles. So can we say that side angle side similarity, these are similar? No, we haven't said the S's yet. We've toyed with them, we've identified them, but how do we say that they actually are in the same proportion? (24 times 12 equals 6 times 48. 144 times 2 is 288 equals 288. And please note, this number, the 288, is of no significance in this problem whatsoever. It's not the area, it's not the scale factor, it's not the altitude, it's nothing other than what verifies that both ratios are the same proportion. But since they're the same, that gives us our two S's. We got the vertical angles for the A. Therefore, by side angle side similarity, these two triangles are similar. So I'm going to go with SER is similar to what? Don't say it out loud, but make sure you can find which triangle matches with SER. Count of three, let's do a choral response. Everybody please tell me what triangle it is on the count of three. 1, 2, 3. Very good. GEF. Any questions about demonstrating that triangles are similar using side angle side similarity? Yeah.
Like, you did like 24/6.
Uh-huh.
What's the difference between doing like 24 or 6 over 24?
No difference whatsoever. Nope, not at all. As long as you're consistent. I did kind of big triangle over little triangle. And I did that here and then again here. And if you had done it the other way, that would also be fine. So let me take you off on a little discussion about that for just a second, because I think that is important. Do you remember the other day I talked about, did I do this with you guys? Like if you buy a 6-pack of soda, it's $3, let's say, Safeway soda. And then let's say that you buy a single one for 50 cents. You could set up a proportion here. You could say that 6 cans at $3 is the same as 1 can at 50 cents. And is that a valid proportion? Could I also say that 6 cans is to 1 can as $3 is to 50 cents? Could I also say that 6 cans is to 50 cents as 1 can is to $3? So this is the point of this little discussion. How do you know which proportions you're allowed to set up and which ones you aren't? So here's what I like to think about. If you look at what's horizontally aligned, in this case, the 6 and the 1, and the 3 and the 50, do the 6 and the 1 conceptually have something in common? What do they both refer to? The number of cans. They're the same type of number. Do the 3 and the 50 cents have something in common? They're both numbers or price, right? Price or value. Then take a look at the stacks. Is there something about these two that makes sense? Aren't they what you discover on the shelf where they're selling 6-packs? And what about these two? They're on the shelf where they sell singles, right? So these numbers have something in common. These numbers have something in common. These have something in common. These have something in common. Therefore, this is a correctly set up proportion. However, when I come down to here, what does 6 and 50 cents have in common? Nothing. 6 is from this part of the shelf, and 50 cents is a different part of the shelf and its number value. So if in fact we've got two triangles, and let's say 4, 5, and 6, and 8, and 10, and 9, and I were to set up, okay, so I'm going to go 4 is to 8 as 6 is to 9. What's true about 4 and 8? They're the smallest sides, aren't they? What's true about 4 and 6? They're the smallest triangle, right? What's true about 8 and 9? They're the bigger triangle. What's true about 6 and 9? Nothing. This is a flawed proportion I've set up because 6 is the largest here and 9 is the middlest here. If the horizontals match and the verticals match, then you're good. In this case, my vertical doesn't match. Okay. You're going to have a page here of homework to do to practice some of these things. And then the last part is your favorite. Proofs. Give you a choice. You want me to do 1, 2, or 3 for you? 3, all right. We're going to do 3. Anytime we do a proof, how do we start? Givens. Please keep the conversations down. We're almost done. Anything else I can put in here? I got another given, right? But let's hold on that. What can I put in this bottom line? Where do we know we're headed? Okay. Triangle WXY is similar to triangle VZY. How many possible things could go here in the reason? Is it infinite list? Very good. It's one of those 3. It's got to be. It wouldn't be AAA because that's what AA similarity means. We don't need the third angle. The 2 is enough to give us that. All right, so what else do we know? We know that WY bisects XYZ. So what does that mean? Yeah, Kate. Hold on for a second. Kenny, go ahead, Kate. Very good. Then angle XYW, this one over here, and angle ZYV, this one over here, are congruent. Why is that true? Yeah. Should I write that? Because it bisects?
No, it bisects that. No, it bisects that congruent.
Yeah, that would work. If angle bisector, then congruent, or we could just say definition of angle bisector, right? That's what it means to be an angle bisector. Don't mind my mix of capital and lowercase letters. All right, so that gives us one piece. We know we've got an A now. So we're not going to do SSS. We could do SAS similarity, or we could do AA similarity. What else do we see in here? And this is weird. This is why I'm showing you this one. We haven't used this yet, have we? It's part of the given that we didn't use. Let's use it. XY over ZY equals WY over VY. Given. But what does that tell us? Yeah, Braden.
Wait, but why is like that without flips? The definition of equal bisector doesn't start off the given.
So I chose to put this part of the given here, and then I chose to pull out the information that's relevant from it before I muddied the waters and brought in the second part of the given. Right? They're 2 separate givens. They're separated by a semicolon here. What does this thing say? What does this tell us? Yeah. That the ratio of these sides is the same. In other words, these two sets of sides are, what's the word? No, not similar. Nope. Nope. Proportionate, thank you. These two sets of sides are proportional. In other words, their ratios are equal. And if those sides are proportional, then doesn't that give us one S here and a second S there? So that's all we need. We now have enough to say side angle side similarity. QED, we're done. And I will tell you that when you're doing SSS proofs and SAS proofs, similarities, you kind of always get these types of things given to you. It's hard for you to establish that side lengths are proportional without being given that they're proportional for this level of geometry. Okay, you've got the rest of the period. If you have any questions, please come on up. I suggest you work together. If you have any outstanding test efforts you want to take, today we've got 40 minutes, so it's a good time to do that. If you want to come take the test, come on up, let me know, and we can arrange that.